of algorithm analysis. After we understand what is the algorithm, the definition of an algorithm, and some issues related to algorithm, and also the overall perspective of algorithm. Now we are going to uh, discuss on the fundamental of algorithm analysis. Meaning we go specific to the algorithm analysis, the first component. As I mentioned, we have two main components. The first is analysis, the second is design. Okay, now we go to fundamental of algorithm analysis so that you can have some background of the analysis. What is the analysis? Okay. Okay, these are important problem type as I introduced just now, and here I give you the uh, a bit detailed explanation of the problem type. The first is sorting. What is sorting? Basically, sorting is rearrange item of a given list in certain ordering, whether ascending, or non-decreasing order or non-increasing order. Okay, this is the sorting. Meaning you have the item, you need to rearrange, reorder the item in a given list. We have the list, inside the list we have the item, we need to reorder in terms of maybe ascending or descending. This is sorting, right? And the second is searching. Searching, dealing with finding a given value called a search key. We have a search key called K. Normally we use the K, and after that we have the list. We need to find the K whether inside the list, and we have to find for every index. If we put into array, start with that 0, 1 until the m minus 1, whether we find it or we didn't find it. Okay, this is the searching problem. So dealing with dealing with finding a given value called a search key in a given set or multi-set. Okay. The next is string processing, or sometimes called string matching. What is a string processing? Typically involve comparing string, or called string matching. So like we compare alphabets, characters, the text in others, in simplest way we call the text, but in computer science called string. String is actually more to the text. We want to compare text and try to find the matching text. This is called the string processing. And the fourth type is called graph problem. This is quite tough. It's a quite also common and important problem. Any problem that can be represented by a collection of points called vertices, and they are connected called edges. So we have vertices and edges, and we connect through what is vertices by using the edges. And the problem with this, the main is traversal, where we need to traverse from point to other point, and that called the traversal. And we have the classical traversal algorithm, as you I think learned through the data structure, where we have the basic post order, pre-order, and post order, pre-order, and pre-order. Post order, in order, and pre-order. Those are the algorithm for traversal, classical traversal algorithm. We have others, a lot of graph problems, and also the algorithm. Okay. And next is combinatorial problem. This also quite tough algorithm, quite tough problem, and also quite complex. So what is a combinatorial problem? A more complex problem that asks to find a combinatorial object. So such as permutation, we have three of the combinatorial problem in terms of categories, subcategories. We have permutation, combination, and subset. And this basically you have to go back to the mathematics in order to understand this permutation, combination, and subset. It's involved with factorial, right? So we have a lot of the problems under this combinatorial problem. Okay. Next is geometric problem, dealing with geometric object such as point, line, and polygon. This requires certain the basic understanding of the geometric, especially those who are interested in, more to the core fundamental of the multimedias. So you have to understand this. This is the basic. And finally, numerical problem, dealing with mathematical object of continuous nature, like your functions. For example, solving equations and system equation, computing different integral, built-in function, and etc. Where we have just now, GCD is fall under this numerical problem. GCD Euclid algorithm is under numerical problem. Okay. Okay. Now desirable characteristic of an algorithm. what is desirable characteristic of an algorithm? Okay, we have 3 desirable characteristics. Number 1, the algorithm must be efficient, must be efficiency. Mean efficient in terms of what? Time efficiency will be discussed thoroughly for this subject, and space efficiency, not a big issue nowadays currently, because space we have enough memory size in order to implement our algorithm. So our main concern is time efficiency. So our syllabus actually we cover this, how we're going to do the analysis so that we can know that the algorithm is efficient or not based on certain benchmark. What we call just later on called big O, big omega, big theta. And the second desirable characteristic is simplicity. What is simplicity? You know, Datuk Siti Nurhaliza product, simplicity, right? It's a very simple. Basically, we need to provide or introduce algorithm or design algorithm with a very simple algorithm, simple step, but work for complex algorithm. That is our desirable characteristic. Okay, look like very simple, but also can work for any problem, even a complex problem. And the third is generality. What is generality mean? The algorithm can be generalized. Generalized mean where we have the algorithm, the solution, and this algorithm can be used to any application. We can apply to any case study. That called the generality. Understand your generality? Let's say
Yes.
any question. Generality. No question.
No, sir.
Okay. Generality, for example, taking sorting as an example, very simple. We have algorithm for sorting. And if this algorithm, let's say bubble sort, we call it is generality, fall under generality, doesn't question. Because the bubble sort can be used to whatever, to apply whatever application. Let's say you want to apply sorting for numerical, also can be used. Let's say we want to apply sorting for alphabet characters, alphabet like text also can be used, or maybe for others. That called the generative. Maybe sometimes we just design algorithm very specific to that application. We cannot generalize for others application. That called the algorithm is not generalized. Mean not under the democratic algorithm, which is generative. Okay. Okay, step of algorithmic problem solving. Okay, the first, this is the step in general. So the first step, you need to understand the problem. Of course, you need to understand the problem and also some of problem. Not some, basically all the problem basically come from the mathematical problem. That's why you need to understand the mathematics. Okay, understand the problem, and next is decide on conditional mean, whether it is exact or approximate solving. As I mentioned just now, the problem, we have 2 types of problem in general, whether the problem is exact problem or approximate problem. Exact problem requires exact solution. Like sorting is exact problem. When we solve it, so automatically we can solve it exactly, mean the problem can solve it accordingly. Mean sorted, okay? Sorted items. So that is exact. Approximate, basically we cannot get the exact solution, like combination problem, we cannot get the exact solution. So we need to aim for the optimal solution. And the next is data structure. Of course, data structure is important. When we try to implement, we need to know certain data structure, especially when to implement the sorting. So we need to write it, or we need to put it into the array so that we know how to use the array. Okay. And finally, algorithm design technique also, you need to decide on algorithm design technique. Which algorithm, which design technique is suitable to solve the problem. Okay. Next is we design an algorithm. We design an algorithm in terms of what? In terms of pseudocode, or we design algorithm in terms of pseudocode based on certain design strategy. And next is proof correctness. After we design, we need to prove whether our solution, our algorithm is correct or not. Based on two, as I mentioned just now, whether number one is based on the experiment, number two based on mathematical proving. Okay. And finally, after we prove the correctness, we need to analyze the algorithm in the sense that we need to know that whether our algorithm is efficient or not in terms of time as well as in terms of space. And finally, after we finish all this step, the final step, we can code the program. We know how to write the algorithm. That's why we need to understand the programming language here, and we can implement it. Regardless any languages you can use, it doesn't matter because the language is not the big issue. You can use whatever language you know and just implement it. Okay, this is actually a step of algorithm problem solving. Okay, any question? Ada soalan? Tak ada. Okay, kalau tak ada, we move on to this. What is an algorithm design technique? After you know a bit on the analysis, now I give you the overview. What is the algorithm design technique? And algorithm design technique, sometimes called strategy or maybe sometimes called paradigm, basically the same thing, is a general approach to solve problem algorithmically that is applicable to a variety of problems from different areas of computing. This is the definitions of the algorithm design technique. So method of specifying algorithm, we have two ways here, whether through the pseudocode. What is a pseudocode? A mixture of natural language-like construct, which is basically there's no, restriction here. You may use any language like Melayu, Bahasa Melayu, Jawa and so on. You can use to describe your pseudocode. It's a mixture of natural language-like. Or maybe you can specifying the algorithm. You can specify the algorithm by using the flowchart. A method of expression and algorithm by a collection of connected geometric shape containing description of algorithm step. So basically in practical, we may start with flowchart first to get the idea, start, and after we have the input, process, output, and finally with that flowchart, you translate into pseudocode where you put the step 1, step 2, and so on. And finally from the pseudocode, you can translate it into pseudocode. And finally, you can implement the algorithm. Okay. Why do we need algorithm analysis? Basically, this is the same thing. I think what we did discuss just now. I think I will skip this. The same thing to measure how good the algorithm, to benchmark lower bound optimality, and finally as a mechanism to compare and choose the appropriate algorithm for further implementation. Okay, analysis. I think this is the same thing as we discussed. Issues like correctness, timeliness, specificity, optimality. Approaches, we have to approach with the theoretical analysis or empirical analysis. You know what is the difference between this theoretical analysis and empirical analysis? Someone please respond. What is the difference? Theoretical analysis and empirical analysis?
Theoretical tu macam teori je, empirical tu lebih kurang macam implementation.
Okay, ingat empirical je, bukan? Okay, betul, in general, but theoretical basically based on the theory based on mathematical analysis, based on mathematics. Without implement the algorithm. Empirical analysis, we have to implement the algorithm, we have to conduct the experiment, you have to record the time. After you record the time, you increase the number of the data and you plot the diagram. See that the graph. That is empirical analysis. Okay, don't worry. Later on, I will explain again. But now you just understand theoretical analysis actually based on mathematical analysis, or in particular we call it asymptotic analysis. Okay, empirical analysis basically you have to conduct the experiment, record the time, and plot the graph to see the difference when we increase the number of data or we increase the n input size. Okay. Okay. Now, before we move on to the analysis, to the detailed analysis, we need to understand this term called complexity. How complex is? So basically, in general, there's no way to measure or to claim that the problem is complex based on certain what? The based on the implementation, the source code. Let's say when we write the code, when we write it, let's say the number of line may be 1,000, then we can conclude that it is complex. No, because that one is a very subjective. Some programmers maybe can write very few line, maybe some others maybe 1,000 line. It depends on your skills or experience. Okay, that's why complexity we cannot measure it based on the problem is quite abstract based on the source code, based on the algorithm. So the complexity basically we can refer to the rate at which storage or time grows as a function of the problem size, typically n. This is how we can discuss on the complexity based on refers to the rate at which storage or time grows as function for the problem size. Typically we denote as n. Two important measures as I mentioned just now, time complexity or space complexity. Okay, space. So our main concern is time, not space, because space nowadays we have enough space. Actually, we have enough memory size. But for the time, still the problem we cannot solve it because it depends on the complexity. I mean the nature of the problem and also the implementation and in terms of design, for example, to solve the problem. Okay, can be measured by two mechanisms, whether machine independent or machine independent. Machine dependent or machine independent. Okay, what is machine independent? Machine dependent. The absolute growth depends on the machine or compiler used to execute the algorithm and the other factor. Machine dependent, in simplest word, I can say that this mechanism is depends on machine, depend on computer. It is empirical analysis. This is empirical analysis where we need to write the program, use certain machine, certain compiler, and conduct the experiment. We record the time. This is called machine dependent. Okay, this is how we can measure the complexity based on machine dependent. Based on empirical analysis. The same thing. Don't get confused with it. Okay, machine independent is really empirical analysis. In machine independent, the growth is expressed by the complexity in terms of its relationship to some known function based on a proportionality approach and commonly known as asymptotic analysis. What is machine independent? In simplest word, I can say that it doesn't depend on machine, doesn't depend on the computer and experiment. So to measure the complexity here is based on the asymptotic analysis, which is actually mathematical analysis or theoretical analysis. So relate to back to the just now we had empirical, which is actually machine dependent. Theoretical analysis actually is machine independent, which is based on mathematical analysis or theoretical analysis, in particular called asymptotic analysis. Okay, clear? Don't get confused with this term, two terms. Clear?
Clear, Doctor.
Okay. Okay, now asymptotic analysis. What is asymptotic analysis? Is a specific mathematical analysis. It's an area of under mathematics called asymptotic analysis. So this asymptotic analysis actually fall under machine independent, or we can say that it is a theoretical analysis. Okay, so now asymptotic analysis, based on the idea that as the problem size grow, because why size grow is we want to estimate when we have the certain size, we start with what we denote as n. We start with certain number, let's say n equal to 5, increase 10,000 until the million. When the size grows, the size of the n, mean the sample or the data or maybe the input size grows, the complexity will eventually settle down to a simple proportionality to some known function. That's why under asymptotic we have this function incorporated in the big O. We have the big O, big omega, and big theta. Okay, what is a big O? Big O relates to an upper bound of on complexity. Big omega relate to a lower bound of complexity. Big theta relate to a type bound of complexity. Okay. Just now someone asked me about the lower bound. And now we're going to discuss on the detail. What is the lower bound? What is upper bound? What is the type bound? Based on this function called big O, big omega, big theta. Okay, don't worry. Okay, before we go further, we discuss further. I think it is good if you bit on the understand bit. What is asymptotic analysis? Okay, in mathematical analysis, asymptotic is a method of describing limiting behavior. What is limiting behavior? We want to observe certain behavior when the input size called n increases until infinity. When n get large, what is the behavior when increase the n? So this is actually the area of asymptotic analysis, the study of it. We want to observe asymptotically the limiting behavior when the n increases until get large or until infinity. That is asymptotic analysis. So in computer science, in the analysis of algorithm, it is to consider or estimate the performance of algorithm when applied to very big input data set. Here. So meaning that our complexity is actually not based on the problem. Not based on the problem exactly, but based on the input. If we have the input and our input grows until certain amount, which is actually anti-infinity, become bigger and bigger and bigger. What is the behavior? Can the algorithm means in terms of time can handle that the time when we increase the input size, the data, for example, the data set will increase. This is the issue under the complexity or specifically under the asymptotic analysis. So it's a study to the behavior of the input when they are very large, considering a function. General partial f of n is when there is a need to describe its properties as n become very large. So maybe you when you are doing COP FYP, maybe you just use a very small data, small input size. So there's no issues. If you increase data, like nowadays we have the big data, right? This is the issues of the analysis. Whether it is the algorithm is efficient or not. Okay, if f of n here, the function general function, when we want to estimate the n here, when increase the n until infinity or until n get large, approximately, let's say when we do the analysis, end up with n squared. After you do analysis, let's say we get this n squared. So how does it mean? How are we going to interpret this? So the function of n is said to be asymptotically equivalent to n squared as n get into infinity. So let's say after we do the analysis, end up with n squared. Now we don't know how to do the analysis, right? Don't worry. But when we do the analysis, end up with n squared, the answer with this, then we can interpret that is asymptotically equivalent to n squared as n get large until infinity. So we can conclude that if the algorithm fall under n squared, when we increase the input size until whatever numbers until infinity, so that is the upper bound, only n squared. So only n squared. It cannot go beyond that n squared, exceed that n squared. That is actually the meaning of this analysis, the asymptotic analysis. Okay, understand? Okay, in estimating the running time of an algorithm, we may end up the asymptotic behavior as the growth of f of n, the function here, where n actually our main constant n, the input size, as n get large. For example, a function of f of n, we obtain this c is some constant time n squared time k, another constant for some constant factor of c and k. And it said this algorithm to be asymptotically equivalent to n squared as n get last. Okay, meaning that if we end up with this after we do the analysis, we have the sum constant. Let's say maybe 100 times n squared times maybe 1000. This sum constant, whatever. And finally, we can conclude that asymptotically equivalent to n squared only. We can basically omit or ignore the constant here. Because this constant, we increase the n, it become constant. 100, always 100. 1000, always 100. But the n become variable and it will increase. But the limit is, the limiting behavior for this actually n squared only. So for this case, it cannot go beyond that n squared. This is actually the conclusion can be made through the analysis. Okay. It is not important to know the constant factor, as I mentioned just now, because they wouldn't affect the upper bound or lower bound or type bound of running time. For example, if we have this function, we obtain 3 times n squared plus 100 here. Actually, we can conclude it's only n squared. Okay. Maybe you still don't understand. Don't worry. After this, I will explain again why you get this, and maybe you can relate back to the the statement here. Okay. Okay. Order of growth. So order of growth mean from minimum from the lowest until the highest order of growth. So most important order of growth within a constant multiple as n increase get large or get infinity. Example, how much faster will algorithm run on computer that is twice as fast? How much longer does it take to solve the problem of the input size? This is actually the question raised when actually when we know that the order of growth later on. Okay. Okay. This is the order of growth or efficiency class. Basic efficiency class. Start with the O1. 1 is actually constant. What does it mean here? When we increase the n, it won't increase the time. The time becomes constant. When increase the numbers of n, the input size, so the time become basically constant. Let's say if n equal to 1 millisecond, we increase n into 10, also 1 millisecond. We increase to 1,000 million, also 1 millisecond. So this is called constant factors. Okay, constant factors. Or the second log n. So you increase like log n function, logarithm, or maybe n is a linear. When increase n, let's say tens, we increase the sample, the size n is 10. So let's say the time taken 1 millisecond, and after that increase 20, the time taken 2 millisecond, 33 millisecond. When we plot, the diagram become linear. That's called the linear time. And we have others, n time log n. We have n squared called quadratic, and to power 3 cube, and called cubic. And we have 2 to power n exponential. We have the n factorial, which is the highest. This from the lowest until the highest here. This called the order of growth. Okay, we use the order of growth here. This become the benchmark to know whether the algorithm is efficient or not. And the n factorial here is actually the most pure algorithm, which is not efficient. This actually the efficient. The most efficient is 1 log n followed by n until the n factorial here. Okay. Okay, this is the details explanation about the O1, big O1. The T here is here too. This denote general function. T is time, running time. N is our main concern. When n increases until certain numbers, certain limit, which is until infinity, what is the behavior of this? If T of n here equal to O1, which is the constant just now, this is called constant growth. T of n does not grow at all as a function of n. It is a constant. For example, array SS has this characteristic. The operation AI, whatever I is in that 0 until whatever, take the same number of steps no matter how big A is. So let's say you want to retrieve the value of inside the array. We are given let's say I equal to 1 million. We just go straight to the 1 million. So basically there's no increase on term of time. Basically the same thing. So in the real world problem, there's no algorithm actually fall under this or one, but under the efficiency analysis or basic efficiency class. So this is actually the first class, mean from the lowest. And the second is T of n equal to big O of log n. This called logarithmic growth. T of n grow as the base 2 logarithm of n. Actually, the base doesn't matter. It is just rational to use base 2 in computer science. For example, binary search has this characteristic. Okay, so this actually based on log n function. So after this, I will show that the diagram you can see clearly. Okay, I just read this first, and after that, I will explain again. And third is T of n or big of n. This called linear growth. T of n grows linearly with n. For example, looping over all the elements in a one-dimensional array would be an O n operation. And next is n time log n. This called n log n grows. T of n grows as n time the base 2 logarithm of n. For example, heap sort and merge sort have this characteristic. That's why merge sort, I think you know already, the BO is n log m or n time log m, or simply called n log m. Okay. And next is T of n big O of n to power of k. This called polynomial growth. T of n grows as the k power of n. Selection sort is an example of a polynomial growth rate. Again, it is O n squared. Maybe this n k is k equal to 1. K equal to until whatever. This called n to power of k. Here this called polynomial growth. Whether n squared, n cube, this actually part of the polynomial growth. And next is T of n equal to big O of n to power of n. This called exponential growth. T of n grow exponentially. It is pronounced big O of 2 to the n. Exponential growth is the most feared algorithm pattern in computer science. Algorithm that grows this way are basically useless for anything but for every small problem. You can use this algorithm when this algorithm fall on this for the small problem, but when we increase the numbers of input size becomes not efficient. I mean the most feared algorithm. You cannot solve it within the certain normal time. But any other positive constant could be used to express the same idiom. And finally, T of n of big O equal to big O of n factorial. This is called factorial growth. T of n grows factorially. It is also the most feared algorithm pattern in computer science. Okay, look at this. Maybe from there you can understand. This is n. When increase n, let's say n equal to 10. If log 10 here 3.3. If this 3.3, let's say millisecond, we can consider this 3.3 millisecond only to take to complete the process of n. And if n log m 3.3 times 10, if n squared 10 times 10 is 100 millisecond, so is n cube is around 1000 here. And if 2.n to 10 to about 3, if n factor like 3 times 6 times 10 power of 6. This is how we can see that these are from the lowest here until the highest here. In terms when we increase the here, and when we increase the n here to the 10 power of 10 squared here, this become n log n 6.6 10 squared and 6.6 times 9 and so on and so forth. And when we increase, let's say here, this 10 power is a 1 million n simple size. If log n only 10, 20, and after that we cannot calculate here. This is actually quite a long time to complete, maybe years, maybe 100 years to complete the process. Okay, and I think from diagram here we can see that this is a pattern. If O1 here, this x and y, this x exists is actually for the n input size until get last here infinity. When we increase this until whatever infinity, and we can see that time here, running time here, whether increase or not here. Okay, for the O1, when increase the n, it won't increase. That's why we get this straight line. All the n, the pattern like this, increase a bit, and linear increase accordingly. Okay, n log n, n time log n increase. Higher than O n. Of course, n squared higher than n log n, and this n cube and this n factorial become like this. That's why this factorial, this polynomial. So this polynomial basically factorial here is the most fit algorithm. Okay, this is how we can measure the complexity, benchmark the complexity of the algorithm. Okay, look at this. Let's say we have this. When we do the analysis, let's say this input size n10, we increase m power 1, 2, 3 until here, and we increase 10, 100, 1,000 and 10,000 here. Let's say we do the analysis, we got this. This is some constant 60 times n squared plus 5 times n plus 1. So if we substitute this with the here n size, the exact numbers, exact input size, it becomes 6,051. If we take only this, we take all the constant and the n's, we take only one constant here, 60 times only this, and when n squared only this. Okay, and finally we can see that how it increases and the pattern grows like this. Okay, and this actually, when we plot the diagram here, maybe you can see the pattern here increase accordingly. When we take this constant, all the constant 60, so the pattern like this. When we take one only constant 60, the pattern like this. And when we take only the n here, maybe we can see the pattern. But we can see that more or less basically the same pattern increase. And when we try to plot the diagram here from 1, 2, 3 here, this actually how we can, this actually the first diagram where we consider all the constants, 65 here. But here we only take one constant 60, and third is actually we just take n only. So when we plot the diagram here, we can see that here basically the same pattern. The conclusion can be made from here, where basically we just omit, we ignore all the constant because the constant won't affect that the analysis. We can only, our main constant is only the n only. Okay, the n only. Okay. There are two functions denoted as P of n. Okay, I think we stop here because I think next lecture I will explain again so that you can understand this the theory. But from now, can you understand the asymptotic analysis, the n, the order of growth?
The smallest one is the most quickest lah between all the counter analysis. Is that correct?
Which one?
Maksudnya macam yang jadi kalau ikutkan yang paling laju sekali logaritma lah.
You are talking about order of growth, right? Yeah.
So maksudnya daripada atas tu paling laju lah sampai yang bawah tu paling lambat macam tu.
Yes, correct. Correct. Mean in term of efficiency, yang atas paling efficient. Okay. Any other question? So like this lah. So katakan n ni equal to 10 input size. So kalau ini convert, let's say we consider this as 3.3 is millisecond. It take millisecond for tens for each. So this only 3.3 millisecond. Kalau n fall under n, 10 millisecond. Mean 10 input, 10 millisecond. So you increase accordingly, right? Kalau it fall under n log n or n times log n, 3.3 times. So n squared 10 times, 10 squared here. So this how basically the input size. This from the lowest, from the efficient to the most fit algorithm to the highest times. Clear?
Clear, Doctor.
Okay. Let's say satu algorithm sorting, bubble sort analysis shows that n squared. What do you mean? What do you think? What does it mean? Is it efficient? Is it complex in terms of complexity? Any response? Let's say we have a bubble sort, right? Satu algorithm bubble sort end up with n squared. Satu lagi algorithm called merge sort end up with n log n time log n. Okay, the first question, which one actually efficient? Bubble sort or merge sort?
I think merge sort.
Merge sort. So, based on the order of growth, of course, n log n actually less than n squared, right? So, of course, n merge sort is more efficient compared to bubble sort. Because in terms of order of growth is n time log n. Because n time log n is less than n squared. Clear?
Clear.
So next is how to do the analysis. Sekarang you tak tahu macam nak buat analysis, you tahu dah ada order of growth ataupun kita panggil efficiency class. So kalau kita buat analysis nanti end up with n squared atau end up dengan n log n atau n atau whatever, then we know that whether the algorithm is complex or not. So this n squared, katakan end up n squared tadi, the upper bound actually n squared, which is actually whatever the numbers of input given to that until infinity, the maximum only n squared. Cannot beyond that. That is the upper bound. Kan? Maknanya, let's say katakan bubble sort tadi, you try to improve, you claim that. You self-claim, kata, oh, you punya algorithm efficient. You have to do the analysis and finally, you kena analysis end up with less than n squared, maybe n log n. And then baru you kata you can improve the bubble sort. Otherwise, you just self-claim without any evidence, scientific evidence. That is the benchmark. Ataupun tiba-tiba you run bubble sort, kemudian you kata, oh, bubble sort sampai n cube. Then your claim is baseless. Sebab teori kata memang the maximum n squared. You cannot, whatever the numbers of input size until infinity, millions, the highest only n squared. That is the upper bound. Understand? Boleh? Boleh faham?
Boleh.
Okay, lagi 5 minit. Any other question? We stop until here, until this. Okay, until this. So maybe next week we continue this so that this are a bit tricky to you, so that we stop first. Later on, I will explain again the detail here. Any questions, Soba? Ada soalan? Ada soalan? Tak ada?
Tak ada, sir.
So far okay, clear, atau masih confused?
So far so good.
So far so good, okay. Yang lain? Kalau confused is okay because this still introduction. Later on when we go through, I mean week by week, after finish certain analysis, then insyaAllah maybe your understanding become better and better. Okay, kalau tak ada soalan, you may leave this session. Kalau you ada soalan, you may stay and ask me. I will wait until the last person leaving this session. Okay, thank you very much. See you next week.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you, Doctor.
Selamat berbuka.
Thank you, Doctor. Selamat
Selamat
berbuka.
buka, Doktor.
Ya, sama. Jangan
Have a
buka
nice
sekarang
day.
ya. Tunggu azan maghrib.
Thank you, Doctor.
Sama.